Here's the function for number 3. Part A asks you to find the vertical or horizontal asymptotes. So since our function is a fraction, the vertical asymptotes come from where the denominator equals 0. So we can set the denominator equal to 0 and solve for x. We get x equals 1. So there is a vertical asymptote at x equals 1. For the horizontal asymptotes, that's where you're comparing the degrees of the numerator and denominator. The degree is just the highest exponent. Since both the numerator and denominator are being squared, that means the highest exponent is 2 for both the numerator and denominator. So I had to look it up. Here's my sticky note of when you're comparing the degrees, if the degree of the numerator is greater than the degree of the denominator, there is no horizontal asymptote. Skip down here, if the degree of the numerator is less than the degree of the denominator, there's a horizontal asymptote at y equals 0. If the degree of the numerator equals the degree of the denominator, which is what we have here, you have a horizontal asymptote at the leading coefficient, the fraction of the leading coefficients. So in this case, our leading coefficients, the coefficient on these x's, they're both 1. So y equals 1 over 1, which equals 1. So we have a horizontal asymptote at y equals 1. Okay, part B is asking to state all the intervals of increase or decrease for the function. Increasing and decreasing comes from the derivative. So we need to take the derivative of this function. I'm going to go ahead and move to the back of my page. So we're starting with x plus 2 squared over x minus 1 squared. It's going to be easier to take the derivative if we write it this way. So y prime, because it's a fraction, we're going to have to use the quotient rule. So we've got the derivative of the numerator, which is 2 times x plus 2 to the first power, which we don't have to write. And then we need to take the derivative of what's inside. The derivative of x plus 2 is just 1. So if you wanted to write a 1 next to that, you could, just to show that you did the chain rule, but it's not going to make a difference because multiplying by 1 does nothing. Okay, and then that gets multiplied by the denominator as is, minus the numerator as is, times the derivative of the denominator. So times 2 times x minus 1 to the first power times the derivative of x minus 1 is also 1. So the chain rule, again, doesn't really change anything here, but you do need to recognize that that is a chain rule function. All of that over the denominator, which is x minus 1 squared, squared. Okay, let's multiply everything out in the numerator. I'm going to go ahead and distribute this 2. So we get 2x plus 4. I'm ignoring the 1. And then x minus 1 squared is x minus 1 times x minus 1. Over here, I'm going to, let's see, we've got x plus 2 squared. So that's x plus 2 times x plus 2. Distribute the 2 here. We get 2x minus 2. Ignore the 1. And the denominator, x minus 1 squared squared, is x minus 1 to the 4th power. Okay. A little bit more work in the numerator. I'm going to do the x minus 1 times x minus 1. So I'm going to leave the 2x plus 4 alone. X minus 1 times x minus 1. You can use FOIL and then combine like terms. You get x squared minus 2x plus 1. Minus x plus 2 times x plus 2. Using FOIL and combine like terms, you get x squared plus 4x plus 4 times 2x minus 2. All of that still over x minus 1 to the 4th. Now to multiply here, you have to distribute the 2 to the x squared, the negative 2x, and the 1. Then you have to also distribute the 4 to the x squared, the negative 2x, to the 1. So everything in this set of parentheses is getting distributed to everything in the other set. So we get 2x cubed. X times x squared would give us x cubed. Minus 4x squared plus 2x. Then distribute the 4 to get 4x squared minus 8x plus 4. Minus, we're going to do the same thing over here, but we need to recognize that we are subtracting all of this. So we're subtracting everything. So let's go ahead and use parentheses here. We get 2x cubed minus, okay, so I'm distributing the 2x right now. 2x times x squared is 2x cubed. 2x times 4x is 8x squared. And 2x times 4 is 8x. Distribute the negative 2, we get minus 2x squared minus 8x minus 8. Okay, rather than write all this all over again, I'm going to go ahead and distribute this negative. So I'm taking away the parentheses. This positive 2x cubed becomes negative, so that minus can stay. Negative times positive makes this, it's really just changing all of these signs. Positive to negative, positive to negative, negative to positive, negative to positive, negative to positive. And all of that is still over x minus 1 to the 4th. Okay, now let's look in the numerator and see if any of those, well, we're combining like terms, but we have a positive 2x cubed and a negative 2x cubed that are going to cancel out. For x squared, we have negative 4, positive 4, those cancel. Do we have any more x squared? We have negative 8 and positive 2. That's going to add to be negative 6x squared. I'm going to go ahead and mark those out just to show that I've dealt with them. For just x, we have 2 and negative 8, which is negative 6, another negative 8, and a positive 8. Okay, so those two are going to cancel out. So really we just have positive 2 and negative 8, which is negative 6x. Mark those out to say that I've dealt with them. Then we have positive 4 and positive 8. So we have plus 12. There's our simplified derivative. Okay, so to find out where the function is increasing and decreasing, we need to set the derivative equal to 0. If your derivative is a fraction, the only time it's going to equal 0 is when the numerator equals 0. So let's set negative 6x squared minus 6x plus 12 equal to 0. We can factor out a negative 6. We get x squared plus x minus 2. Factor this quadratic, x plus 2, x minus 1. So since there's not an x right here, we don't have to worry about this -6. We just set x plus 2 equal to 0, x minus 1 equals 0. So our critical values are at -2 and +1. Okay, if we use a number line at -2 and +1, we're going to test numbers into the derivative. So if we test -3, you can do this in your calculator, you end up getting a negative. You test 0, you end up getting a positive. And if you test 2, sorry. If you test 2, you end up getting a negative. So the function is increasing where the derivative is positive, which is from -2 to 1. And it's decreasing where the derivative is negative. So from -infinity to -2, and from 1 to infinity. So be careful when you're testing your values into a function this complicated. Make sure that you're plugging it in correctly into your calculator, knowing that a negative value, when you square it, you end up with a positive value. In the denominator, no matter what you put in, you're going to end up with a positive value because it's being raised to the 4th power. Things like that, very important to remember. Okay, part C. Part C is asking to identify all relative minimum or relative maximum points. That also comes from the first derivative. So if we look at our number line again, we have -2 and 1. So we've got negative, positive, negative. That means we've got negative slopes, and then positive slopes, and then negative slopes. So it looks like we have a minimum at -2 and a maximum at +1. So it is true that we have a minimum at -2, but it is not true that we have a maximum at +1, because if you look back at part A, we know that there is a vertical asymptote at x equals 1. So we couldn't have a maximum where there's an asymptote on our graph. So we can say there is a relative minimum at x equals -2. If you want to get the y value that goes along with this, plug it into the original function, you get a y value of 0. So again, I'm not sure if she only cares about the x value or if she's going to want the entire ordered pair. So even though it looks like there would be a maximum at 1, because there's a vertical asymptote there, there couldn't be a maximum. So make sure that you're thinking about that when you're writing your answers. Part D. Part D is asking to identify all inflection points. Find all inflection points and determine intervals where the graph is concave up and concave down. That comes from the second derivative, which is given to us. 12x plus 42 over x minus 1 to the 4th. So your inflection points come from where the second derivative equals 0. So for this fraction to equal 0, that would be where the numerator equals 0. So 12x plus 42, we're going to set that equal to 0 and solve for x. So subtract 42 from both sides and divide by 12. Negative 42 divided by 12 is negative 3.5. Or if you wanted to leave it as a fraction, it would be negative 7/2. I think either way would be fine. Okay, so this is our inflection point, or presumably it's our inflection point, but we need to look at the concavity before we decide for sure, because an inflection point only happens where the concavity changes, either from up to down or from down to up. So at negative 3.5, there would have to be a change either from positive to negative or from negative to positive. So let's test values into the second derivative. If you test a value to the left of negative 3.5, so negative 4, you end up with a negative value. To the right of negative 3.5, you get a positive value. Sometimes it's important to look at when the denominator is equal, or when the denominator is 0 as well. So if we look at where the denominator would be 0, that would be when x is 1, which again, we have a vertical asymptote there. I'm really not sure exactly. I think she's going to send, or already has sent, the answers to the review. You may want to double check this with her answers, but in my mind, at positive 1, we have a vertical asymptote. The second derivative is still going to be positive on this side as well. But if you think about what that might look like on a graph, so we've got a vertical asymptote at x equals 1, and we've got concave down, concave up, and then concave up again. So here, let's say this is negative 3.5. The interval where it is concave down, there's no issue there. We know it's concave down from negative infinity to negative 3.5. But in my mind, you couldn't say that it is concave up from negative 3.5 to infinity, because it's not concave up at x equals 1. It doesn't exist at x equals 1. So I would say, instead of writing negative infinity, or sorry, instead of writing negative 3.5 to positive infinity, instead of writing this as one interval, I would write it as 2 intervals, from negative 3.5 to 1 and from 1 to infinity. So we're not including 1 in this interval, because at 1, the function doesn't exist. Okay, so I'm going to say it's concave down from negative 3.5 to 1 and from 1 to infinity.